In this video, we're going to be talking about real and unequal roots of the characteristic equation and real and unequal roots of differential equations. A quick review from algebra: if you have a polynomial, we'll call it p of x, and let's say it's ax to the, I'll just pick a number 5 plus bx to the 4th plus cx to the 3rd dx squared ex plus f. And a through f are just constant coefficients. They're just numbers, real numbers. This polynomial will have 5 solutions. So x equals, let's just call it n sub 1, n sub 2, n sub 3. N is just a real number. It can be an integer, it can be a decimal, it can be a fraction, it can be a complex number. As long as it's a real number. Actually, it doesn't even have to be a real number, right? For example, the polynomial p of x equals x squared plus 1 has 2 roots. X equals plus or minus I. Those are complex numbers. X equals 0 plus 1i and 0 minus 1i. Those are the 2 solutions to that quadratic polynomial. So we have 5 roots, 5 possible roots, and that is, we can tell that just by looking at the highest power of the polynomial. So we know how many solutions we're going to have just based on the power of the polynomial. What we don't know is what type of solutions those are going to be. They could either be real, they could be complex, or they could be a combination. Some real and some complex. If they're all real, then they're all real, right? If you have complex roots, these come in pairs. We call these conjugate pairs. So for example, you would have a plus bi and a minus bi. If one of your solutions is a plus bi, I've used a and b there again, and I really shouldn't have. Let's use different numbers or different letters. Let's call it p plus qi and p minus qi. The reason I've changed that is that I don't want this a, b, and c, right? I don't want the values to get confused with these values. They're not necessarily the same. So if you have a solution that turns out to be p plus qi, you're guaranteed a solution p minus qi. All right. So because those come in pairs, in this particular example, we could either have 5 real roots, or we could have 2 complex roots and 3 real roots, or we could have 4 complex roots and 1 real root. Those are the only possible combinations. In this video, we're going to be looking at just this case where all the roots are real numbers, and in fact that they're equal, right? There's a subdivision we could do here. We could say they're all different, or they're all not different. Some duplication of values. And in this video, duplication. In this video, we're going to be looking at just this subcase here, where all the roots are real and they're all different. Real and unequal roots. Now keep in mind that what we're finding here is the roots of a characteristic equation, and we're going to use those roots. We're going to use the solutions to the characteristic equation so that we can build the solution to the differential equation. Right? Once we have the r values from our characteristic equation, we'll be able to use those in c to the rt, in the various instances of c to the rt that we know are solutions to the differential equation. So on the next slide, I'm going to take a look at the same ideas that we've been talking about, or that we talked about in chapter 3 with second order differential equations, and see how they apply to higher order equations. Let's review just a couple more things here. Let's start by taking a look at an nth order linear homogeneous differential equation. These look like this. It's nth order because the largest derivative that was taken to put this term in place was the nth derivative. It's linear because all of the terms that have a y or y prime in them do not have a combination of y's and y primes. Right? That would make that a nonlinear differential equation. Our equation doesn't have that, so our equation is linear. And it is homogeneous because the left-hand side is equal to 0. It's also important to note that the coefficients here are constants. They're not functions of any kind. They're just constants. They're real numbers. Our solutions to this may not be real, but the coefficients here are real numbers. And none of these a values is 0. None of the coefficients is 0. So that's what makes this an nth order homogeneous linear differential equation. We also know that the solutions to such an equation are going to look like this. The right pen here. Y sub 1 is going to equal e to the r1t. Y sub 2 is going to equal e to the r2t, and so on, so that any solution y sub I is equal to e to the r sub I t. Now all of this is saying is that the i's have to match, but the value y sub I and the value r sub I do not have to match. Once we find the solutions to the characteristic equation from this differential equation, we'll be able to plug those solutions in here, and then we'll build our general equation based on that. The solution to this differential equation will be some constant times the first distinct solution plus a different constant times second distinct solution, and so on, up to, I'm going to go ahead and call it C sub n, e to the r sub n times t. And I've used n there and I here because down here, I was just saying that for any value I, this could go up to n, but I was just saying for any value I, this relation holds true, right? All of these solutions are going to take this form for some value of I, where I goes from 1 all the way up to n. So I don't really need this anymore. All I need is the ith one. Got the wrong pen again. Right? And they all look like that. So I can put this up here. This is my general case. And that's going to lead to a general solution that looks like this. Now, it's important to note that I'm only going to have n different solutions like this if there are n distinct solutions to the characteristic equation. So the roots of the characteristic equation have to be real. No two are equal. And only then can we say we have n distinct solutions to the differential equation. But if we do, then we can say that these functions are linearly independent. And that's when we get to say that the solution looks like this, right? If each of these is linearly independent from the others, then we can write a combination of these solutions, a linear combination of these solutions, to indicate a general solution, because this is not a multiple of this. I can't multiply something times the nth solution, the nth term here, and get the second term. If I could do that, then these solutions would not have been linearly independent to start with, and we wouldn't be able to build this solution, the differential equation solution, this way. But if all of these are linearly independent, then we can do that, and they can only be linearly independent if there are n distinct solutions to the characteristic equation. So let's take a look now at an example. If we take the equation y triple prime plus 5y double prime plus 6y prime plus 2y equals 0, we can write the characteristic equation for this as y cubed, sorry, not y, r cubed plus 5r squared plus 6r plus 2 equals 0. And what we want to do is find the solutions to the characteristic equation. There will be 3 of them because this is a third power polynomial. And so with some luck, we'll be able to find r plus or minus 3 different constants, and that'll give us our 3 solutions. Let's see, how could we go about doing this? The method that pops into my head is division, long division, or synthetic division. I know from algebra that this thing has 3 solutions, and that if it has any rational solutions, those rational solutions must be either plus or minus 2 over 1 or plus or minus 1 over 1, based on the values in this position and this position here. So I'm going to start with positive 1. I'm going to test that to see if it is a root by doing some synthetic division here. 1, 5, 6, 2. I'll bring down the 1, and then I'll multiply this 1 by this one and put it here. I add those and I get 6. Now I multiply the 6 by 1 and I get 6. Add those and I get 12. Multiply the 12 by 1, I get 12, and I get 14 here. This needs to be a 0. If it's not, then this is not a root. So I'm going to start over. I'm just going to erase all of this, and I'll put a different root in there. Let's try negative 1. Just bring down, I forgot to erase my previous work here. Let's get rid of those as well. Okay, now if I bring down the 1, multiply these, I get negative 1. Add these together, that gives me 4. Multiply 4 times negative 1, that gives me negative 4. Put that there. Add those together. Multiply 2 times negative 1, that gives me negative 2. That gives me 0. So that means that my first root here is in fact negative 1. Remember, these are all r minus c or r minus k. So since my root is negative 1, that's going to be r plus 1. Now the other thing that this process does is it tells me that r cubed plus 5r squared plus 6r plus 2 can be factored as r plus 1 times something, but it tells me what the something is. It tells me what the quadratic is that's left over. It's r squared plus 4r plus 2. So now I want to see if I can factor that. I have an r and an r, a 2 and a 1. 1 times 2 there is going to be what gives me that 2 there, but 1r plus 2r is not 4r. So it doesn't factor that way, and in fact it turns out it doesn't factor. So what I need to do here is use the quadratic formula on this quadratic to find out what its roots are. So let's see, I'll leave this here, and I think what I'll do is erase what I've got left here, just remembering this quadratic here that's represented here, and I'll solve that using the quadratic formula. So I'm going to erase this, and I'm going to solve the quadratic formula, solve the quadratic equation. R squared plus 4r plus 2 equals 0 by using the quadratic formula. R is equal to 4, negative 4, plus or minus the square root of, not negative in this case, 4 squared minus 4 times 1 times 2 all over 2 times 1. I do the arithmetic here. I get negative 4 plus or minus the square root of 16 minus 8 all over 2, just negative 4 plus or minus the square root of 8 all over 2, which is negative 4 plus or minus 2 root 2 all over 2, and everything's divisible by 2, so that gives me negative 2 plus or minus root 2. So my two solutions to the quadratic part of the characteristic equation are r equals negative 2 plus root 2 and r equals negative 2 minus root 2. Now I could write these in here. I could say that's r plus, let's see, how do I want to do this? R minus the number negative 2 plus root 2, and r minus the number negative 2 plus root 2, or minus root 2. I could do that. I could write those into the factors, but it's not a Math 99 class. I'm not trying to factor this quadratic equation. I'm trying to find the roots to an equation. I'm trying to find the solutions to the equation, not necessarily factor it. I have it in factored form here because I was originally trying to factor it. So what I'm going to do now is erase all of this work and just write the roots down so we can refer to them. So let's get rid of that, assuming you know how to do all of that. And from this characteristic equation, then I have r equals -1, r equals -2 plus root 2, and r equals -2 minus root 2. I can erase the form that I have this in here, and then just move this up to here. I guess we can put it there. So now that we have the roots, we can write the general form of the solution to this differential equation. We have, let me label these r values, 1, 2, and 3. And remembering that we want our solution to be kind of in that form there, I'll start by writing y sub 1 equals c1 e to the r1t. Well, r1 is -1. You wouldn't necessarily need to write the -1 times t. You could write just minus t, negative t. Y sub 2 is equal to some potentially different constant times e to the power of r sub 2 times t. Well, r sub 2 is -2 plus root 2. And then y sub 3 is a third constant times e to the power of r sub 3 times t. And so our general solution is, I got ahead of myself actually, the distinct solutions do not include these constants, right? The general solution is a linear combination of those, so I get this. C2 e to the -2 plus root 2 times t plus C3 times e to the -2 minus root 2 times t. And that is the general solution to the original differential equation here. So this is my solution. If I had had some initial conditions, if I had, for example, y of 0 equals, I'm going to say 3, y prime of 0 equals 1/2, y double prime of 0 equals -0.27. I'm making those up, and I'm making them a little weird on purpose because they are not necessarily appropriate initial conditions for this equation. My point, though, is that we now know how to solve higher power differential equations. We can use the initial conditions given also to come up with not just a general solution, but a particular solution. I don't think I want to take the time to go through another example like this in its entirety, but what I think I will do is on the next screen, I'll take a look at example 1 in your textbook, which is a fourth order linear differential equation, and it gives the initial conditions. So I think what I'll do there is just sort of step through the same steps that they do in the textbook, but then I'll take a look a little bit more closely at what we do with the initial conditions. Okay, here is our differential equation, and I've put the initial conditions into a box so that we don't let that information confuse what we're doing here. My characteristic equation is going to be r to the 4th plus r cubed minus 7r squared minus r plus 6 equals 0. And finding solutions to this may include using the rational roots theorem. Rational roots can be of the form 1. This is a 1 here, so we have 1 over 1, 2 over 1, 3 over 1, 3 over 1, or 6 over 1. And of course, these can all be plus or minus those values. So I have 8 possible rational roots to consider. Obviously, I'm not going to take the time to do that here, but it might be worth pointing out that since this is a fourth order differential equation, a fourth order characteristic equation, you don't get down to a quadratic until you've potentially found 2 roots, of the of the characteristic equation. So you might have to go through the long division or the synthetic division process a couple of times. But in this case, having done all of that, I can say that the roots are equal to 1, -1, 2, and -3. And with that, I can write the general solution. I think I'm going to erase my 4 potential rational roots here because that's not really informing us anymore, and it's in my way. So I'm going to get rid of those. So my general solution is y equals a linear combination of e to the power of, in turn, r1, r2, r3, and r4, e to the power of rt. So e to the power of r1t, r1 is 1, plus c2 times e to the r2, that's -1, so I'm going to get negative t for my power. c3 times e to the power of r3 times t, and c4 e to the power of r4 times t. There's my general solution, but I have initial conditions. So I want to see if I can find a particular solution. The initial conditions tell me that if I know y, if I know my equation, right, I know the solution, then I can plug 0 in for t and I'll get 1 out for y. So I could find, I could get some more information by doing that. Let's go ahead and do that. If t is 0, I get c1 e to the t, which is 1, plus c2 e to the negative t, that's t, it's still e to the 0, which is 1, plus c3 e to the 0, plus c4 e to the 0. So when t is 0, I get that, and when t is 0, y is equal to 1. I'm going to write that result over here in a slightly different form. c1 plus c2 plus c3 plus c4 equals 1. So I've used this initial condition, but none of the others. In order to use this one, I have to have the derivative of my solution, the derivative of y. Well, I don't have that, but I can take it, right? I can take the derivative of y, and I get y prime equals. Now, remember your product rule and your chain rule and all that good stuff when you're doing these. This is a product. I take the derivative of a product. That's the first times the derivative of the second. We're talking about the first factor times the derivative of the second factor, plus the second factor times the derivative of the first. The first is c1. The derivative of the second is e to the t, right? Derivative of e to the t is itself. Plus, I'm still on this term here, plus the second, which is just e to the t, times the derivative of c1, but that's just a constant. The derivative of the constant is 0. So this should be plus 0 here, but I'm not going to write that because I don't have enough room. The next term, c2 e to the negative t, the derivative of that is the first times the derivative of e to the negative t. Well, e to the t has a derivative of itself, and then I'm taking the derivative of the inside function here. Derivative of negative t is just -1, plus the second times the derivative of a constant, so plus 0 again. As it happens, that's going to be the case for all 4 of these terms. All right, the derivative of the third term is the first times the derivative of the second. The exponential is its own derivative. The chain rule gives me a 2. The fourth term is the derivative of the exponential is itself. The chain rule gives me a -3. So that derivative is c1 e to the t minus c2 e to the negative t plus 2c3 e to the 2t minus 3c4 e to the -3t. But now what I want is y prime at 0, and that is c1 e to the 0, which is 1, minus c2 e to the 0, plus 2c3 e to the 0, minus 3c4 e to the 0. And I'm told that that equals 0. So now I have another little piece of information I can add to my list here. Let me put a line down the middle of this. c1 minus c2 plus C3 minus 3C4 equals 0. Okay, that was the first derivative. Now I need to use this one, so I need the second derivative in order to plug 0 into the second derivative. I need to find the second derivative. So I'm going to take the second derivative, which means taking the derivative of the first derivative. So y double prime, actually I'm going to use this form because it's cleaner. Y double prime is C1 e to the t, the first times the derivative of the second, plus the derivative of the second term. The second term, since I've said plus, includes all of this, including that leading negative sign. Now you could just have pulled that negative sign out front if that's how you see it, that's fine. But I'm going to write this as the first times the derivative of the second, chain rule, that's a negative, plus the second times the derivative of the first. The first is still a constant, so that's that term. Now the next term is the first times the derivative of the second, and the first is still a constant, so no, that's just a plus 0 again. And lastly, I have 3c4, the first times the derivative of the second, e to the negative 3t, I get a negative 3. And I'll clean that up. That is c1 e to the t plus, because I have a product of two negatives here, plus c2 e to the negative t plus 4 c3 e to the 2t plus 9c4 e to the negative 3t. And when I plug 0 in there, I get c1 times 1 plus c2 times 1 plus 4c3 times 1 plus 9c4 times 1. That is equal to negative 2. And I'm told that when I plug 0 into the second derivative, the result is negative 2. So let me add that to my list. C1 plus C2 plus 4C3 plus 9C4 equals negative 2. All right, I'm going to leave myself enough room to write my fourth line there, my fourth derivative result, or my fourth evaluation result. It's my third derivative, because that's the next thing I need to do here. I've got a third derivative that I can evaluate at 0, so I have to find the third derivative first. So far I've only got the second derivative, and I'm going to use this form. This is y double prime. Perhaps I should circle these. I used my original proposed general solution, and then I took the derivative of that to get this. And once I cleaned it up, I got y prime equals, and this was the form of that nice cleaned up form of that first derivative that I used to take the second derivative. And then there's my second derivative, all nice and tidied up, but before I plugged in the 0. And now I'm going to use this one to take the third derivative. So y triple prime is equal to c1 e to the t minus c2 e to the negative t plus 8c3 e to the 2t minus 27c4 e to the negative 3. How did I get a yellow pen all of a sudden? That was weird. Okay, I'm getting there. E to the negative 3t. All right, and I'm told that when t is 0, that's equal to negative 1. So I can write y triple prime of 0 is c1 times 0 minus c2 times 0 plus 8 c3 times 0 minus 27 c4 times 0, and that is equal to negative 1. So that's the fourth line in my system. That's what I've been doing here, is building up a system of equations. Right, so let's write that out. I get c1 minus c2 plus 8c3 minus 27c4 equals -1. Now, this is not a class in linear algebra. If you've had linear algebra before, or frankly, even if you've had sort of elementary algebra or probably intermediate algebra or algebra 2, we spend some time talking about how to solve systems like this. Now, when you're in high school or when you're in Math 141 or Math 99, we don't usually mess with systems that are quite so big and messy. But there is a way to do this on your calculator. Maybe I'll make a separate video for that, just so that I can show you how to do that if you don't already know. But in general, find the solution to this system of equations, and you have the coefficients that you need for your general solution. I'm just going to do that on my calculator, and I'll come back and put those down here. So all of my work here culminates in this. C1 is 11/8. C2 is 5/12. C3 is -2/3, and C4 is -1/8. So in a perfect world, I would take this equation and replace each of these coefficients with each of the values I now know that they're there, that they are. I'm not going to do that here primarily because I don't want to erase the whole screen. I mean, I don't mind erasing it, but I kind of want to leave it as a record of what we did. So I'm going to leave that there, and maybe I'll write the final solution up the side here. That way we at least have the result of all the work that we've done. My particular solution is y1. I'm looking at this general solution, but I'm going to rewrite it with these values I now know for C1 through C4. C1 is 11/8 times e to the t plus C2 is 5/12, so I have plus 5/12 e to the -t. And C3 is -2/3, so -2/3 e to the 2t. And C4 is -1/8, so -1/8 e to the -3t. And that is my particular solution. That is the answer to this problem. The difference between this one and the previous one being that we didn't have initial conditions on the last one that we did, so we couldn't find this particular solution. We had to stop back here. And there's a lot of work involved in this, but we can find a particular solution if we have initial conditions. So I actually made most of the videos for this course at one point, and it's been, gosh, probably close to a year. I didn't quite finish, and so I'm picking up where I left off. And I can't remember if we've done this before, this really long, drawn out, finding the solution to a system of equations. We did it for quadratics. I know we did that. I know we did it for smaller orders of differential equations, but I can't remember if we'd already done it for these higher order. So there you go. There's how you find the solution to a particular solution to a differential equation if you have initial conditions. Now,